In this video, I'm planning on talking about the first law of thermodynamics, or what's basically an energy balance. So for an energy balance, so if we just do a really general energy balance, we know that we have to have some total energy in, and we're going to have some total energy out, so this would be the total energy leaving the system. And then this is just equal to the change in the total energy of the system. We can write this mathematically as energy in, so I'm just using E for my mathematical symbol, and then I have in, minus the energy out is equal to the change in the energy of the system. So this is just the mathematical way of writing what we stated above. And so this is going to be, this is the net energy transfer, and this is the change in energy of the system. So energy is a property, so this E is a property, and properties only change if the state of the system changes. So if we have a process and the state of the system doesn't change, then delta E is equal to 0. So what we want to do is expand on this energy balance equation a little bit. So first of all, energy can be transferred in 3 ways. So energy transfer occurs by heat, work, and mass. And so we can say that this energy in minus energy out is equal to Q in minus Q out. So this would be the energy, this would be the heat in minus the heat out, plus the work in minus the work out, so that's this, plus the energy in by mass minus the energy out by mass. And then this is still all equal to delta E, or the change in the energy. And then this change in the energy, this is the change of the internal energy plus the kinetic energy plus the change in potential energy. So this is the change in the internal energy plus the change in the kinetic energy plus the change in the potential energy. So what we can do, I'm just going to rewrite this equation like this. So energy in minus energy out is equal to the change in the energy of the system. So this is the net energy transfer by heat, work, and mass, and this is the change in internal, kinetic, and potential energy. So really what this is it's 2 ways of writing the same thing. So we can either think of energy as flow work, heat in or heat out, or we can think about it in terms of the change in internal energy, the change in kinetic energy, and the change in potential energy. So this equation can be written a few different ways. So first of all, I'm going to rewrite the energy in minus energy out is equal to the change in the energy of the system. We can write this as a rate form, and remember, a rate form just means that it's per time. So the rate form of this equation is E in dot on top minus E out dot is equal to the change in the energy of the system with time. So this would be the rate, basically the rate of net energy transfer. So rate of net energy transfer, and then this is the rate of change of the energy of the system. And so remember, a rate just means that it's per time. So this would be like energy per second or energy per minute, whatever unit of time you're using. And then we can also write this in a differential form. So the energy in minus the energy out is equal to the change in energy of the system. And notice that these equations are all, none of them are on an as mass basis. We can write all of these on a per mass basis. And what that means is, like for instance, let's take this differential form and write it as little e minus little e out is equal to dE of the system. And this little e is just the big E divided by mass. So we're just writing this on a per mass basis. So we've divided the energy by the mass. And these differential symbols, so this lowercase delta is, this basically represents an inexact differential, and this D represents an exact differential. And these are just used to distinguish whether or not the property that we're talking about depends on the path of the system. So that's something that you'll learn later as you go through the thermodynamics class. But that's what those different differentials mean. We can now, let's write this equation in a little more specific terms. So if we go back to this one, I had written this equation where we had Q net plus work net plus the mass, the energy carried by the mass is equal to the change in energy of the system. So you'll see this equation, like I'm actually going to just write out the entire, I'm actually just going to write out the entire equation again so we can start looking at some different forms of this equation. So we have Q in minus Q out plus work in minus work out plus the energy carried by the mass of the system in minus the energy carried by the mass of the system out is equal to delta U plus delta KE plus delta PE. So what we can do is, first of all, for this demonstration, for this video, I'm going to assume that this is just 0, and I'm going to assume that because I'm going to say we have a closed system. So remember, a closed system means that you don't have any mass flowing in or out of the system, and if we don't have any mass flowing in or out of the system, that means that there is no energy carried by the mass in or mass out because there's no mass in or mass out. And then I'm also going to assume that this is a stationary system, and so what that means is that it doesn't have kinetic energy, it doesn't have potential energy. I'm going to assume that it's so it's like, let's just say this is a container of water sitting on the table. So it also doesn't have a lot of elevation. So we're going to assume that the change in kinetic energy is 0 and the change in potential energy is 0. So let's just say these are 0. So now let's look at some forms of this equation that you'll see. So you'll often see this Q plus W is equal to delta U. So I've just taken this Q in minus Q out and said it's Q, work in minus work out, said it's W, and then the delta U. So this is the form of the equation that you'll often see in chemistry. And so you'll see this equation in chemistry. And the form of the equation that you'll often see in thermodynamics and physics is with a negative W for work. So you'll see Q minus W is equal to delta U. So this is the form that you'll see in thermodynamics and physics to a steam engine. So a steam engine is what thermodynamics developed from, the analysis of steam engines and how to make them more efficient. So what we were interested in with what people were interested in when they were analyzing steam engines was how much work could they get out. So how much heat did they need to put in, so heat in, to get work out. So they were interested in how much work could they get out of this system. So what did they have to put into the system to get work out? So the sign convention is in thermodynamics and physics is that the work out is positive, the work in is negative, and then the heat in is positive, and heat out is negative. So this is the same for the chemistry as far as the heat, because in chemistry the heat in is considered positive, heat out is considered negative, but it's the opposite for the work, because for chemistry the work in is considered positive and the work out is negative. So we've basically swapped the signs for the work in thermodynamics and physics. Basically what we've done, so this equation right here is basically this form. So we have the Q plus W. Basically what we've done with this form is we've said that Q in, so Q net is Q in minus Q out, and work net is work out minus work in. So what I mean by that, let's just rewrite this. So we have Q in minus Q out, and then now we have a minus work, and so we're going, these are basically swapped. So we have work out minus work in, and then I'm just going to leave the mass in and mass out 0 for now, so we're assuming there's no mass flow in or out, so this is equal to delta U. And I do want to take a step back to this equation for a second. This equation is assuming that we have a simple compressible system. And what that means is that we don't have any electric, or we don't have any change from electric work, magnetic work, there's no surface tension effects. So basically we're just assuming that this is a simple compressible system. So the equation that you'll most often see if you, say, Google the first law for thermodynamics, you're going to see this form of the equation. So you just need to recognize what form of the equation you're using, and that's going to tell you what sign convention you need to use for your work. And the other thing with this equation is it's important to recognize that the assumptions we've already made when we use this equation are, first of all, that it's a simple compressible system, so we're not taking into account any electric, magnetic, or surface tension effects. And the other thing we've assumed is that it's basically stationary, so the change in kinetic energy and the change in potential energy are 0. And we've also assumed that there's no energy, there's a closed system, so there's no mass flow in or out of the system. So depending on, like if you use this form of the equation, you want to recognize that you've already made some assumptions, and so if those weren't assumptions you could make for your particular system, then you would need to go back to the more general form of the energy balance and take into account those effects that you have in your system. So let's look at an example problem of how we would use this energy balance to solve a problem. This problem says that we have a vertical piston cylinder device that has water and is being heated on top of a stove. So what I always like to do when I start drawing, or I start setting up these problems, is I like to do a drawing. And this says it's a piston cylinder, so I'm going to draw a piston cylinder. And it says it contains water, so it has water. It's being heated on a stove. That means that there's Q, there's energy in, because energy is being transferred in by heat. And it says that it's 65 BTU. And then it says that the heat losses from the sidewalls are 8 BTU. That means that Q out is 8 BTU. And it says the piston rises as a result of evaporation, and so the piston's moving up, and then it says that 5 BTU of work is done by the vapor. So we're going to have, it says so the work is done, the work is being done by the system, so that means that we have work out is equal to 5 BTU. And it says determine the change in energy for this process. So we want to find the change in the energy. So we have delta E is 0. So let's make some assumptions. First of all, we just have basically a piston cylinder full of water that we're heating. It's stationary, so that means that the change in kinetic energy is 0. And also, it most likely doesn't have very much elevation, so the change in potential energy is also 0. So now let's write our energy balance. So we have the energy in minus the energy out is equal to the change in the energy of the system. Now let's just write out the full equation, and we'll cancel out the terms that are 0. So we have Q in minus Q out plus work in minus work out plus the flow energy in minus the flow energy out is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. So we've already determined that these are 0 because it's a stationary system. And there's no water flowing in or out of this piston cylinder, so these are 0. And then let's look at these other terms. So we do have heat in and heat out, so these aren't 0. We have work out, but we don't have any work in. So we're not putting any work we're not doing any work on the system. The system is doing work on the environment. Okay, so now let's write our equation. So we have Q in minus Q out minus work out is equal to delta U. So really the change in energy of the system is just the change in the internal energy, so that's what we're going to solve for. So now let's put in some numbers. So Q in is 65 BTU, Q out is 8 BTU, and the work out is 5 BTU is equal to the change in the internal energy, and this is equal to 52 BTU. Okay, so we wrote this equation one way using this form, which is basically, this was assuming that we were using Q plus W, delta U. What if we had have used this form of the equation, so Q minus W is equal to delta U? Well, we're still going to end up with the same thing. So what we can do, I'm just going to write out this equation. So we have Q in minus Q out. And then we have minus, because we have Q minus W. And then we have work out minus work in is equal to delta U. So now let's look at this. So we have, so we still have Q in and Q out. We don't have any work in, so that's 0. So we end up with Q in minus Q out minus work out is equal to delta U. So that's the same thing. And then if we had let's say that we didn't write this out, let's just look at how we would put signs into this equation. So one thing to note is if you write these equations out like this, you don't really need to worry about the signs too much. You just need to worry about whether your work is in or out. So you're just putting in, is the heat in or is the heat out? Is the work in or is it out? And sometimes you might not know. So if you don't know, you would just assume a direction. And then if you end up with a negative result, then you know that your assumed direction was wrong. So then you just swap the direction. But let's just look at this equation and look at how we would set up the signs if we were using this equation. So our sign convention, let's just do this over here. So we have Q minus W is equal to delta U. So our sign convention is that Q in is positive, Q out is negative, work in is negative, and work out is positive. So we have we have some Q out, so that's going to be negative Q out. And then we have heat in, so that's going to be plus Q in. And then we have work out, so that's going to be, well, so we've done the Q's, now we need to do the works. So we have minus, because we have Q minus W, so now we have minus, and then we have work out, which the sign convention for that is positive, so we have work out is equal to delta U. So see how we still end up with the same thing. So we have Q in minus Q out minus work out is equal to delta U. So we end up with the same thing as we did using these other forms of the equation. So I think a lot of the confusion with how to set up these problems is regarding the sign convention, because there are several different forms of the first law equation. And so basically what you need to do is just recognize which form of the equation you're using, and then how you're going to just make sure that you're using the consistent sign convention for the form of the equation that you're using, and you should end up with your problem set up correctly with the correct signs.